Okay, when talking about optimization, the real challenge is oftentimes finding the equation that you're supposed to optimize. And in a problem like this one, they've done the work of giving you the equations so that you can answer the questions C, D, and E, which are essentially the optimization questions. The real challenge is coming up with these equations on your own. So the way these questions are phrased, they ask you to explain the relationship between the variables and explain where the area function comes from. So if you can't, you can still answer the remaining questions. But I'd like to focus most of the time on this particular lesson, figuring out how to come up with these particular equations. Challenge for some students is they look at the equation and try to work backwards and see where each of the numbers in the problem come from. But as you can see, we talk about 1 liter is the only given information, and the rest we have is the radius in centimeters and the height in centimeters. Well, where does 1,000 come from? Where does 2,000 come from? And why is r in the denominator? These are things that are hard to answer just from looking at the paragraph. So um, to get parts A and B sorted out, what we need to do is practice this technique called specializing, where we don't work with variables right away. We simply work the problem out with fixed values for the independent variable. The first thing we have to do is figure that out. So here we see h is a function of r, the radius, and here we have area as a function of r, the radius. So that tells me that I need to play around with the r value and radius of the cylinder and see what effect that has on both the height and the surface area. So first, to try to get that understood before we start doing any math. And the idea here, first of all, is our volume is given as a liter and our dimensions are given in centimeters. We need to make some quick conversions because 1 liter is 1,000 milliliters and 1,000 milliliters is 1,000 cubic centimeters. That's the metric system. Now we can connect our volume in liters to our measurements or dimensions of length and height and all that in centimeters. But the real big idea is this idea that if we're going to make a can that has to hold a fixed volume of 1,000 cubic centimeters, as we change one of the dimensions, say the radius, that's going to force the hand of the other dimension. So for here, for example, the height of this can has to get really tall if I make a small radius, because that's the only way I'm going to fit all 1,000 cubic centimeters into the cylinder. On the other hand, if I choose a large value for the radius, that's going to make a very large disk, and it's not going to require as much of a height for that can to hold the same amount of stuff. So one thing I understand in this equation, whatever I choose my radius to be is going to have an impact on my height, and if I was to choose my height, that's going to have an impact on my radius. So they're indelibly tied because of this 1,000 cubic centimeters fixed volume. And what this equation shows me is that if I increase the radius, that's going to decrease the height. And if I decrease the radius, it's going to increase the height. And that's what's being said in this picture as well. So now to explore, what is the relationship between the height and the radius and how can we discover it? In order to do so, I have to take the given information, which talks about capacity, which to me means volume. We establish the volume as 1,000 cubic centimeters, and therefore we start with a volume equation. We have to either look it up on the internet or in a book or find a way to know, but volume is the area of the base, pi r squared, times the height. And if the radius were 5 centimeters, then I can draw a picture that sort of represents that to the best of my ability, and then we understand that there's 1,000 cubic centimeters times or equals pi times 5 squared times the height, which is the thing that I don't know. If the radius were 10 centimeters, I would have 1,000 equals pi times 10 squared times the height, which I don't know. In each case, then, we end up with a simple algebraic equation where h is the unknown and everything else is known. And so to solve for h, I just divide both sides by, in one case, 25 pi, and in the other case, 100 pi. Reducing those fractions gives us 40 over pi for one height, and 10 divided by pi for the other. And quick decimal approximation gives us a height of 12 centimeters for the first cylinder and a height of 3.18 centimeters for the second cylinder. So it confirms my suspicion that a larger radius will require a smaller height, smaller radius will require a larger height. So now all we have to do is see if we can generalize that. So to generalize it, I actually have expressing height in terms of r It's simply a matter of going back to our volume equation. We substitute 1,000 in for the volume, and that's what we know. And then even if I don't know what r is, I can still divide both sides by pi r squared and produce this formula. So that's the first part of the question, which says explain why the height is given by h equals 1,000 over pi r squared. Ultimately, I got to the understanding that I could express volume in terms of radius and height using my volume formula, and then I just do solve. I solve for height by dividing by pi r squared, and that's where that formula comes from. Now comes to the rest of it. What about the surface area? So to understand surface area of a cylinder, it's just to imagine a soup can. A soup can has got a circle for the top and a circle for the bottom, and if you peel off the label and unravel it, you end up with this rectangle. So we have to imagine this rectangle wrapping around the outside of that circle, and that's where the sides of the can is. So the side of the can is really just a rectangle, where the length of that can side is the circumference of the circle, 2 pi r, and the height of the can is the height of the can. So the dimensions of, or my surface area, are two circles and a rectangle whose dimensions are height times 2 pi r circumference. So in the first case, when the radius was 5 centimeters, I had two circles and a rectangle. The height we established was 40 over pi. The circumference of the circle is 2 times 5 times r, or 10 pi. So to figure out the area, the surface area of the can, I take one circle, area pi r squared, another circle, area pi r squared, and then I take the height times the length, and here we see that the pi's divide out, and we're left with 400. 50 pi is approximately 157, so we can approximate 557 square centimeters is the area required if I choose the radius to be 5 centimeters. The last example, or the other example, was a 10 centimeter radius. We have larger circles this time and a much narrower strip for the side of the can. That's going to give me 10 pi, or 100 pi, plus another 100 pi for the bottom of the can. And then we see we have a much smaller surface area of only 200 square centimeters. So what we lost in the side of the can, we gained in much larger circles. And we have two of those. That's caused my area to be 828.3. Going back to the initial question, recall that what we're looking for is value of r, the radius, which makes a as small as possible. Clearly, choosing a radius of 10 is going to provide almost 300 or over 2 or 300 more square centimeters to make that can than if I make r smaller, like 5. So that's probably more optimal. Now, if you actually look at this, you can see that the same process is repeated whether we use 10 or 5. And so these are specialized forms trying to understand the problem. But now I can generalize in forms of variables. So we have the variable r representing the radius, and we have the variable h representing the height, which is expressed in terms of the radius. So earlier, we found how height can be expressed in terms of the radius. And if we look at our formula, it actually starts out as um, pi r squared plus pi r squared plus 2 pi r for the length and h for the height. But instead of using h, I use h in terms of r, which produces this area equation, pi r squared plus another pi r squared, plus we can divide out the pi's and divide out one of the r's to get 2,000 over r. So this is now a formula which actually produces the surface area. If I go back to the original question, discover that that's exactly what I was supposed to have. What I want to point out to you about this is I actually looked at my goal as to find a formula for the surface area, and then I went back at the end to see that it is the goal that I wanted. So I really didn't use this to answer the question. I tried answering the question from scratch, and then I used the problem to make sure I checked my answer, that I did the work right. What's left is simply a matter of, well, ironically, the simple matter is calculus. In order to find the minimum value, we could of course use technology, and as you can see here, 5.419 is the radius value that gives me the least amount of surface area possible, 553.6. To do calculus to get that result, I would need to take the derivative of this function. So first I write it in power form, take the derivative using the power rule, set the derivative equal to 0 because that's the point when the surface area stops decreasing and starts increasing again. Setting that equal to 0 gives me, I add 2,000 over r squared to both sides of the equation to get here, multiply both sides by r squared to get here, divide by 4 pi to get here, and take the cube root of both sides, and finally I get 5.42, which again, confirmed by my graph. And I substitute that back into the original area equation, right up here, and I get 553.6 square centimeters, the minimum surface area. Notice when I chose the radius to be 5 centimeters, I got 557 square centimeters, and if I go just a little larger, 5.4 centimeters, I require even less square centimeters to produce the can. So if I want to make a can that holds 1,000 milliliters or 1 liter of liquid, I would need to, and took the smallest amount of surface area possible. These are the dimensions that would be required. You could also find the height by using the height formula. Anyway, there you go.